All right, we will start here with number 1, which gives you a histogram and starts by asking you to write a few sentences describing the distribution. Anytime you're asked to write a few sentences describing distributions or comparing distributions, probably a good idea, a good clue that you are using shape, center, spread, which is exactly what they're looking for. Shape, center, and spread. Shape, they're looking for you to say that it's bimodal or has 2 peaks. Saying symmetric was not enough. Specifically, you needed to point out that there were the 2 peaks in the histogram. Then your center was right around between the 200 and the 250. Again, it's based on the histogram, not using the table underneath. And then for spread, you could talk about your interquartile range. You could approximate that. You could talk about the range of values. You could cite standard deviation. A few different ways to talk about spread, but shape, center, spread. And as always, it should be in the context of the question. So you should be talking about room sizes, or you should be labeling your numbers as square feet. Any of those are making use of description in the context of the question. Part B, down here, it asks for you to determine whether there are any potential outliers. So we're going to use the 1.5 times interquartile range rule, which is 177. Take the interquartile range, Q3 minus Q1, multiplied by 1.5, that's 177. So we add that to Q3, subtract it from Q1, and we have our upper and lower boundary. So we add it to Q3, we get 469. Anything above that would be an outlier. We subtract, we get -3. Anything below that is an outlier. Turns out none of them are above that upper boundary or below that lower boundary, so we don't have any outliers, which results in this box plot. And remember, to make the box plot, you are using minimum Q1, median Q3, maximum, and plotting those. That's your box plot. And the characteristic in the histogram that's not in the box plot, the main thing that a box plot does not tell you is shape, particularly the fact that we have these peaks in the histogram that you can't tell just from looking at the box plot. So that bimodal shape is the main thing they're looking for you to point out there in part C. Moving on to number 2. Number 2 asks you about the design of this experiment. So first of all, the treatments are the concentrations. So there were 4 different concentrations that they were giving. That's the treatments that we are putting in. On, what are we putting the treatments on? The experimental units, which is the group of insects in a container. And there are 20 of those, or the containers. But you needed to be specific that that's what we are applying the treatments to. And then the response variable that we're measuring, we're using those treatments and comparing. What's the variable that we're comparing between those 4 treatments? It is how many insects are alive after a week. And that's stated right at the end of the question. So that is your response variable. Do we have a control group? A control group is basically the a treatment that doesn't have any change or effect that we think shouldn't affect as a baseline of comparison. So does this experiment have it? Well, yes, it does. It has the group that has 0 milliliters of concentration as a baseline of comparison. And then it asks us to describe the random assignment process. So here's one way to do it. And this involves drawing slips of paper out of a hat. The main thing you need to make sure that you do is to make sure that each treatment has the same number of units, which is 5. You want to make sure that your method, whether it's a random number generator or drawing slips out of a hat or a random INT on the calculator, make sure that it will result in 5 going into each group, and which 5 go in which group is chosen at random. So that is your process on a random assignment. Number 3. Number 3 is your probability question. So first off, we read the first 3 numbers from the table. Probability that the person will be someone whose response is never and a woman. Never and a woman, we just find that section of the table. The section of the table that's never and a woman is the 0.0636. Then we have the person never or a woman. Never or a woman, well, we know that the probability of A or B is the probability of A plus the probability of B minus the probability of both. So we add in the sections that are never, the section that is woman, but then we just double counted the ones that are never and a woman, so we subtract that away, and that gives us our 0.5864. And the last part, it says the response is never given that the person is a woman. That's a conditional probability, never given woman. So out of all the women, how many of them said never? So out of all the women, which is the 0.53, how many said never? That's the 0.0636. So since I know they are a woman, I only want to focus in on going out of all the women, how many of them said never? And that's how we get the 0.12. So are the events independent? Well, now that we have this calculation of never given woman, the easiest way to do this is to say that the probability of never given woman should equal the probability of never, which it actually does. Never given woman is 0.12, and the probability of never is 0.12. Therefore, by definition, those events must be independent. Another way to show this is that the probability of A and B is the probability of A times the probability of B, which indeed it is. Either way, you have to justify it with some kind of calculation. Remember that the idea for independence is that knowing one outcome doesn't affect the probability of the other outcome, which is this definition, that the probability of never given woman equals the probability of never. Because if I tell you, the idea of independence is if they responded never, if I ask you about the chance that they respond never, it shouldn't change after I tell you, by the way, this person is a woman. That chance that they responded never is still 0.12, even though I told you that they were a woman. That is by definition that telling me about one of them doesn't affect the chance that the other happens. And that happens in the other direction too. If I tell you they responded never, the probability that they're a woman doesn't change. So any of these calculations can be used to justify that those events have to be independent. And then part C, we have a binomial distribution. It's a binomial distribution because we are selecting 5 people. We have 5 people. We have the probability of a success, probability of the thing happening every time, which is 0.54. And we have a set number of times the thing happens, which is 5. And we're keeping track of how many times they will always take the medicine as prescribed. So we have a set number of trials. We're keeping track of how many times the thing happens. So that's a binomial distribution. N is 5, P is 0.54. Make sure you define those, N and P, when you say that it's a binomial distribution. Number of trials, probability of the thing happening. And you can either show the formula, at least 4, means it could be either 4 or 5. You could show it that way. Or if you're using the calculator, then remember it needs to be binomial CDF of 3, because binomial CDF is about everything less than or equal to the amount. So if you want greater than or equal to 4, then we need to use the complement and say what's the opposite of that. Well, the opposite of greater than or equal to 4, of 4 or more, is going to be 3 or less. So we find that 3 or less and then take 1 minus it, and we're left with 4 or more. But binomial distribution is the idea there on part C. Moving on to number 4, which is your 4-step problem. And in this case, this is a 2-proportion z-test. 2-proportion z-test because we are comparing the new and the old, the 2017 and the 2014. And it's a proportion because we're looking at the percentage of each of the samples that were resistant. So that's how it told you that it was proportions, and we're comparing these two different proportions. And it's a one-sided test because we're looking for there to be an increase in that proportion. So that's a one-sided test, and the new should be more than the old. The 2017 proportion should be greater than the 2014 proportion. So your alternative hypothesis should reflect that. Random, normal, and independent. Remember, you need to check random, normal, and independent for all of the samples. So for both samples. So for example, in the normal condition, then you should be checking n times p and n times 1 minus p being at least 10 on both of these. And same thing for random and independent. Down here, here's the formula for your z-score. And remember that when we do our 2-proportion z-test, we need a pooled proportion because this standard deviation is based on our null hypothesis. So if it's based on our null hypothesis, then our null hypothesis is that these two proportions are the same. So we're going to have one big proportion that we are calling p hat sub c, the pooled proportion, and this is in your formula sheet. So we are treating it as one big sample. Instead of separate samples of 52 and 61, we're treating it as one big sample of 113. And we know that out of that, 32 of them were resistant. So that's our pooled proportion that's going to go in the standard deviation formula. So then it's the sample proportions minus our null hypothesis is that this difference is 0 over our standard deviation. And we want everything above that since it's a one-sided test, so that's your p-value. Which means that we're going to reject the null hypothesis because the p-value is less than our alpha level. We're going to reject the null hypothesis. There is enough evidence that we are more resistant in 2017. Question 5. This one's about normal distribution. So the first thing I did was I stated out that it's a normal distribution. Here's the mean, here's the standard deviation. And we want to know the 25th percentile because we want to know how many months 25% of the batteries will no longer work. So we want to know when everything underneath it is 25%. That's a percentile. So we can set up that z-score or set up inverse norm in some way. Might help you to draw a picture of the normal distribution and know that the area to the left is that 0.25. Either way, that's where we're getting the 24.604, is setting up and just solving that z-score formula. Then in the next one, we're going the other way. What's the probability that we're within 24? Now we're given the value. We want the z-score. We find the probability, which is 0.2266. Hopefully that should make sense because we got the 25th percentile being a little bit above 24. So that means the percent that are less than 24 should be less than 25%. There's your normal CDF command. But remember that if you're just putting a normal CDF command, you need to define what these things are. This is your lower, this is your upper, this is your mean, this is your standard deviation. You need to say that. I always suggest drawing a picture on your normal distribution questions. And then for part C, gain of $50. We're going to use that answer from part B. Gain of $50 if they do not need a replacement, and a loss of $150 if they do. So that's your expected value. Value times probability of it happening. Add them together, and then the interpretation on average over the long run, here's how much they're expected to make. Next one, finally, question 6. Question 6 did the practice this time of throwing a new term at you and seeing how you dealt with it. So it threw this term of bootstrap median at you, and use what you know about medians, use what you know about sampling, use what you know about sampling distributions and confidence intervals to still be able to work with this term that you've never seen before. And in fact, you did not need to know about what a bootstrap median was in order to answer the question, because you just needed to know what a sampling distribution is and what a confidence interval is. Those are the important parts to being able to answer the question. So first off, part A. Part A, what is the population? Well, the population that we can generalize to is the population that you sampled from. And so the sample that we took was out of all the one-bedroom apartments from the website. That was specifically the group that we sampled, so that's specifically the population we can make conclusions about. Then over on part B, it gave you that distribution and said the typical amount. It asked you to explain why the mean is a bad idea, and it's specifically because the mean is going to be pulled above the median. Mean gets pulled in a direction of skewness when we have a skewed distribution. So those small amounts of very high values are going to push that mean upward, that make the typical apartment price look more than it actually is. Part C, sampling distribution. The way we can do a sampling distribution is to take all possible random samples of size 50 from the website and calculate whatever parameter we're asking about, and that would be the sampling distribution. Every possible sample of the same size would give us our sampling distribution. So then they approximated that process and found all these different medians and asked you to find the 5th percentile and the 95th percentile. Again, percentiles are percent of the values that are below that amount. So if I want the 5th percentile, I want 5% of the values to be below it, which means that it's going to be at the 750th data point. Since there were 15,000 in our sample, then the 5th percentile should be at the 750th data point so that 5% of the values are below it. 750 is 5% of the values. So we count up and we find that the 750th data point is at 2,500. And the 95th percentile should have 95% of the values below it. 95% of the values is 14,250. Or you can say that it's 5% of the values above it, which takes 750 away from it, leaving the 14,250. Either way you count it up, that's where the confidence interval, or that's, jumping ahead. That's where those percentiles should be. Okay, then we're going to get to confidence intervals. So then in part E, it asks what percent of values are in between those two, and it wanted the exact amount. So the percent of values that are between 2500 and 2950, well, we can just add up all the values in the table, which comes out to 14,404. And that is the percent of values that were in that region. So, by definition of a confidence interval, we can use that percentile to get an estimate of that low value and that high value and say we are that percent confident that the true median price is between these two values, which is the interpretation of a confidence interval. And they took either saying that 90% of the data is between here because we did the 5th percentile and the 95th percentile, or using that 96% that you got in part E. So either of those ideas worked fine, but that's just using the idea of the confidence interval, which is that we are using and saying, here's where 90% of the values are, so 90% confident that the actual parameters between those two. That's what a confidence interval is. It uses all the samples that we could collect. These are the percent of the samples that would capture that actual value. So really what it's trying to get you to is, do you know what a population is? Do you know what a sampling distribution is? Do you know what a confidence interval is? Do you know how to find percentiles? Don't get intimidated by it throwing a new term at you.